all really special, and they are all really different. Yeah? And so let's have a look what do you see there. So there are many images, and almost all of them are MRI images, although they are kind of really different. Yeah, if you look at them, so you can see there's something which is close to CT. Is it close to CT by sight? Yeah, and you can see there's something close to angiography. Yeah, and you can see there's something close to R&D. Like remember these pictures about human brain in Alzheimer's disease? Yeah,
Yeah.
and these pictures, they are kind of fused images, remember fused images? Or something kind of duplex images, something like this. So we can see some color on a gray foundation, a gray background. Well, sometimes this is something like this. What does it look like? There is gray picture, anatomy picture, color scheme, and some kind of graphic.
Triplex.
Yeah, it looks like triplex. Yeah, by side. I mean, by side. The content is completely different. By side, it looks like this. And this looks like nothing familiar to us. Yeah, something very special. And all these pictures are MRI. All these pictures are MRI, except one. There is one CT picture. Can you figure out where is the CT picture? Which one? Yeah, the first one, this one. Yeah, this one is CT. And let's figure out how to recognize a CT picture in majority cases. Yeah, what will be the rule? How to recognize CT picture? Can you explain me? Can you suggest me how to feel that this is a CT, not MRI? How do you guess that this is a CT? What do you pay attention to? Any ideas? What is specific? What is special in CT? The color scheme. The color scheme. Yeah. So this color scheme is X-ray color scheme. It depends on density. Yeah. And so what is the basic rule about color scheme which depends on density? What will be the colors?
Black.
Yeah, black will be for air,
and
white will be for bones, and gray
Gray.
will be for
Soft tissue.
Yeah, for soft tissue. So this is really simple rule. So if you are hesitating, if you see some fancy picture, yeah, and it doesn't look like ultrasound, we can recognize ultrasound because ultrasound pictures have special shape, yeah, and we cannot mix with anything, yeah. So if you see some picture like this, yeah, transfusion of water in all the tissue, and this is a way how we can see lesions sometimes in MRI. So this is very interesting approach, and we never use it in any other discipline, and so that makes it even more interesting. So if we go to this color part of these pictures, so like remember what we usually code with color. Like remember R&D, fused images, like Doppler thing, like color Doppler. What is usually about? If you see something not in like black, white, or gray, but in red, blue,
trees, veins.
it's usually function, physiology, function, physiology. Basically, yeah, they do it like this. So this is our concept. They usually show anatomy in white and black, yeah, and we prefer to show like function and physiology in this specific color. So this is just for separation of understanding and for keeping an idea that this is about function. Well, let's see what we can see there. So there are interesting approaches. So this picture, this looks much the same like Alzheimer brain, like for example with FDG or something like this. Yeah, remember FDG? Yeah, this is like PET study with glucose, yeah, for tumor seeking, and not only tumor. Remember, usually we can see a clear picture of brain also. And what do you see there? These are perfusion pictures. So we just see perfusion, yeah, and the color means is it perfusion good or bad. And the reason how we can see perfusion and the technique how we can see perfusion is completely special in MRI, completely special. Because usually when we are trying to study perfusion, remember I showed you a couple of perfusion maps in CT. There were perfusion maps, like these color pictures, yeah, of the lungs, for example, yeah. So in this situation, they usually need, again, to administrate something. So perfusion we study in CT, for example, or an R&D. Yeah, that means that we are administrating something. Yeah, and we are looking how the bolus, yeah, of this contrast media or of this pharmaceutical is going through. And you know what? In MRI, we can skip this moment. We can skip the necessity of using a contrast media, and we can just use something very special. We can create something like a magnetized bolus of red blood cells. Just make them magnetic, like special magnetic, and just follow up how this magnetic stripe is going through the place, the area which we want to study. And so that is what we can do in MRI. So it was completely interesting and new. So these fancy pictures, these and these, which looks like kind of duplex or like a fused image in RMD, yeah? So what's this? This is what we name functional MRI. And functional MRI is the technique, yeah, which helps us to see working and resting areas of the brain in different colors. Yeah? We can get from them different signals. How can it's possible in MRI? The reason is that they have different amount of oxyhemoglobin. Yeah, usually the working area of the brain, yeah, it uses more blood, yeah, and so we have more oxyhemoglobin, yeah, in this place, and different types of hemoglobin and also oxyhemoglobin, they have specific magnetic properties, and that's why we have a possibility, yeah, to get different signals from these areas, and we can show, yeah, the areas which are working. For example, look at this picture, yeah, so we see, yeah, several areas of working brain, yeah, and they show us which area of the brain is busy when the person is speaking or moving its hand or something like this. And what is interesting, if we combine this with anatomy picture like this, we see tumor there, so this white area is a tumor, and we see the functioning area, yeah, the person fulfilling some tasks we ask him to do. And so what can they do? We can compare, yeah, and we can get a clear picture what the tumor is close to, and when we'll plan the treatment, yeah, so we can take this into account and be really accurate in our the activities, and we can see these necessary zones, yeah, so that to have a good result. So when we are treating a patient with brain tumor, so technically it's possible to remove any tumor from the brain, almost any tumor, but usually we cannot do it because, yeah, will damage the surrounding tissues, and the person will be really like completely damaged, yeah. And so if we have this information, we can look more accurate. So this is also very interesting. So what this is what is named magnetic resonance spectroscopy, yeah. But in this situation, yeah, what was the spectre in triplex study? What does the spectre shows us in triplex study? A set of velocities inside the vessels. And in MRI, these spectros, yeah, it shows some chemicals inside of the tissue, some metabolites, yeah, inside of the tissue, which are important for functioning and which can be showing us different lesions. And so why do they have this ability? Because some metabolites, yeah, which contain different chemicals, yeah, they can have different magnetic properties, and we can recognize them using MRI. So this is also really special. And probably the most fancy pictures is this. Can you get any guesses? Give any guesses? What's this? What's the structure?
Thyroid.
Any guesses? Use your imagination. The area is, what is the area?
Maybe thyroid.
No, not
Thyroid.
Maybe brain. So this is brain area.
Brain area.
And what is the structure?
Hemisphere.
Brain hemisphere. Is it?
Basics of magnetic resonance investigation. Words are really important. And we'll start the discussion what is about nuclei, yeah, what is important about magnetic and about resonance, step by step. That is the beginning. So this is what I made preliminary note, just explaining of these three basic things. So first of all, what does it mean that we are speaking about nuclei? Why is it nuclear magnetic resonance? Well, simple thing, because, yeah, the participants of this thing are nuclei of atoms with odd number of nucleons. Well, what are nucleons? Any ideas? Yeah, these are elementary particles of the nucleus, like protons and neutrons. Yeah, just probably the term is new, but you know all this. Yeah, magnet using magnetic fields which are acceptable for research on a live person. Actually, in MRI, since we are trying to study really weak magnetic properties, we have to use strong magnetic fields, and that means that they are using fields which are measured in Teslas. How big is Tesla? Is it a strong magnetic field? Have we any idea? 1 Tesla, is it a strong magnetic field? Or but usually we know that there is something like our Earth magnetic field, how it's comparing with 1 Tesla. Is it bigger or smaller?
Bigger, I think.
10,000 times smaller. 10,000 times smaller. So when we are performing MRI, we are using really strong magnetic fields. There are even restrictions. So in some countries it's like not higher than 3 Tesla. In some countries not higher than 7 Teslas. In some countries there are some research machines which use 9 Tesla, but this is exception. So these are just 2 machines in the world. Basically, machines are restricted like 3 Teslas, and so this is pretty high magnetic field, and this is the field which can only rule the hydrogen magnet because it's the smallest, the weakest magnet, So this is why we prefer hydrogen, the first point. And another point is, since again, the magnetic properties of hydrogen are really, really weak, we cannot study them like using and paying attention to one nuclear. We need to have like milliards and milliards and milliards of nuclei so that to get some measurable signal from them. And so that is also why we use hydrogen, because there are milliards and milliards of hydrogen nuclei inside our body. So that is because, so this is that we choose hydrogen because it's okay, so it's technically okay, And another thing, why do they choose hydrogen and why do they study hydrogen? Because this is really interesting, because hydrogen in our body is inside really different molecules, really different, many molecules, and a really, really different chemical environment, And so that means that we can have different signals from different tissue, like in a really, really big spectrum, And so to get these fancy pictures, we have real possibilities because, we use hydrogen like the source of information. Like pay attention, for the chemical surroundings, in MRI we use this fancy word lattice. It's from chemistry, and it came from chemistry because nuclear magnetic resonance began in chemistry, and so we just borrow it. We never use about the body like we have some lattice inside, but in MRI we use this word because it's from chemistry. And so let's figure out what can they study if our source of information is hydrogen. So we'll use it hydrogen to get special response. So in order to get special response for hydrogen, we have to study tissues which have like a big amount of hydrogen, and the hydrogen which is possible, which has ability to rotate, So, and what are these tissues? These are soft tissue. So MRI is a soft tissue study. Soft tissue study. We can get signals. These special, these specialized response, these selective response, only from hydrogen. So we can study soft tissue. And what about bones and air? How do you think? How do they behave?
Bone is hard. Like
They are
maybe
not tissue with sufficient amount of hydrogen, and they don't have hydrogen which can freely rotate, especially bones. And so that means that they are silent on MRI. They don't respond. They don't produce selective response. And so you're right, they will be black on any magnetic resonance procedure. So remember ultrasound. Does it look kind of the same? We can study soft tissues and we have problems with bones and air. Well, some similarity, but there is a big important difference. Remember what air and bone do in ultrasound. They works like walls. We cannot see through them. We cannot see behind them. Remember this acoustic shadow artifact, But how about MRI? How do you think?
see.
They are just loosened from MRI. We can see through bones. We can see brain without any problem. We can see everything inside pelvis. We can see soft tissue details in all joints, no problem. And so that is really interesting in MRI. So that is really different in MRI. So, well, even sometimes, surprise, you will think that you see bones in MRI, especially vertebral bodies. They are kind of visible. But what do you see actually is not bones. This is bone marrow response. Bone marrow response. Bone marrow is soft tissue. Yeah? And we can see response from soft tissue. That is how it works in MRI. So this is very special and very interesting. So if we speak about soft tissue, let's emphasize that there are two tissues which are very special from point of view of MRI, and one tissue which is extremely special. I'm speaking about water and fat, and especially water. And so what does it mean? That with this tissue we can work more than all other tissues, and we can even sometimes can have pictures which are basically based on water. For example, remember, diffusion image control parameters of both constant magnetic field and both alternating magnetic field. We can control them, we can choose the right one, we can choose them differently, and we can organize, especially this thing, this alternating magnetic field, we can organize it in a very different manner. And so this is also really helpful, and helps us to see different color schemes in magnetic resonance. So what for? We use constant magnetic fields for agonizing weak magnetic properties and to make them measurable. And the higher is the magnetic fields, the better will be the organization, and the better the signal, the better the information. And so basically, like high field MRI machines, they are better than low field in quality, and then their possibilities to show tissues. And what is alternating magnetic field? This will be electromagnetic waves, and this will be radio frequency waves, like radio waves. So radio waves, they're also electromagnetic waves, but what is the difference between radio waves or, for example, X-ray or gamma ray?
Frequency.
Radio waves are non-ionizing. And so what is resonance? Resonance is something which occurs only under certain conditions, so only in special situations, or you can say that this is a selective, really bright, special response to an external stimulus in case, like some conditions coincide, so you can say that that there are some things which can be resonance in everyday life, like sometimes we can say that about information, so this is a highly resonance information. In what case the information will be like this? When it's kind of something coincide, so it's kind of important to this group of persons, and they say, okay, I'll hear this, I'll take this into account because this is important for me. So like resonance in idea, so this is a good way to something to recognize, to see something like in a bright manner, because this is very specific, very bright selective response. And another thing which is important, so this occur only in situation, there is some coincidence, and there is no response, there is no conditions, no certain, like for example, if I'll say to you, like something like you have no exams this sessions. And if I say something like this to a person on the street, well, students in this building which will have no exams this sessions, what they'll say? Okay, no reaction, so this is how it works, So let's see how it works in physics. Do you have any physics understanding what is resonance in physics? So what is resonance? Something what happens when frequencies of two oscillations coincide. Well, I don't know what is the classic example in Indian schools, like in Russian schools, the classic examples about resonance is about like a group of you, everybody has kind of experience of going on a swinging like this, swinging.
Okay.
Can you explain me how to have fun swimming? Like what you have to do? So like try to keep in mind that this is something which has three keep in mind, like simple steps. They are not simple. They're really complicated if to go deep inside. But just to keep the idea, yeah, you can figure out like 3 simple steps. Step 1, yeah, so that to have this, yeah, selective response, nuclear magnetic resonance, selective response. What do we have to do? First of all, we have to put the protons or spins or hydrogen nuclei, these are synonyms, inside constant magnetic fields of the machine. Yeah? And this is for their organization, so that to like putting them on a starting line, something like this. I'm here. Yeah, this is the answer. Yeah? Organization, simple organization. This organization is necessary, but it is not enough. So that, yeah, to make these nuclei able to shout what they are, yeah, to explain in what tissue they are, we need to pass them some energy, yeah, and so they use this radio frequency energy, this radio frequency pulse or sequence, to excite them, yeah, and this excitation leads to some changes in the condition, like this. He turned his head some direction. Actually, the hydrogen nuclei, they do something like this, so they are tuning, yeah, they're changing their position, yeah. Yeah, and pay attention that this happens only in case, yeah, their rotation, yeah, has the same frequency like the radio wave. On this situation, only we have this resonance, and we'll have this nuclear magnetic resonance thing. And in order to measure this excitation and to understand what they are saying, they are ready to shout, and right now we have to listen to this shout, what they're shouting, what they're speaking about. We need to turn off this radio frequency pulse and to follow and to watch their returning into the starting position, or in physical language, their relaxations. Yeah, so they're relaxing, having a face, something like this, relaxing, getting energy, yeah, in like opposite direction. And these 2 steps are necessary so that their magnetic properties can be like revealed, yeah. So before they have these magnetic properties, but they are kind of secret, we cannot measure them. And this is necessary, yeah, to measure, yeah, these magnetic properties. So frequenization, yeah, like getting into starting position, yeah. So this is starting position, and this is before starting position. So not in magnetic fields, yeah, the magnetic properties inside our body are organized like this, in a relaxed manner, yeah, or like this, like people in a crowd, yeah. They are just looking in any direction. And magnetic arrows inside of the body, yeah, these small magnets, are orientated chaotically. Like how comfortable for them, yeah? But when they put them out the body inside the strong magnetic field, yeah, and basically, yeah, some magnetic machines, they are like organized like this. Remember this thing? You probably have this in physics class at school. Yeah, like horseshoe magnet. Did you have this fun, like using it like to play with some magnets or some metallic stuff? Yeah. And this is kind of the same thing, but just bigger, much bigger. Yeah. So that some machines are organized like this. They have this big horseshoe magnet inside. Yeah. And so what is going on? Yeah. So these magnets, yeah, they are hearing this signal, this command. Yeah, like stand all in one line, yeah. And so what they are doing? They are aligning along, yeah, this vector of this magnetic field, yeah, of this magnet, yeah. And that means like they're doing something like this, looking in one direction, yeah, like oriented in one direction. Well, actually, remember, they are rotating, yeah, they're rotating. And that means that actually they are not just steel magnets, they are rotating like this, yeah, like these spinning rods, yeah. But yeah, the summarization of this magnetization looks like this. So they are rotating, but along the magnetic field, and so inside this magnet, the body gets some small magnetization along this field, yeah. Pay attention that this rotation is non-synchronous, or we name it out of phase. What does it mean? That means that every magnet is doing it like this.
Spinning rotation.
They are not showing like the same time on the clock. Like they are not doing it like this. This is synchronous in phase, but they are doing it like this, not showing the same time.
Spinning.
Yeah? And so that is this preliminary step, organization. So they are just stepping in line, something like this. They're looking at the same direction. Yeah. So this is number one, step number one. Again, remember this is not enough. This is just preliminary. They still have no strength to tell about them, and we need to add some excitation to this. So what do? We use this radio frequency wave. And in case, the frequency is the same, so there is this excitation thing, this excitation event, and see what's going on, when we are using this pulse, what is going on. These magnets, they are step by step rotating more and more synchronously, like from out phase they are going to in phase. They need energy for this, so this energy we transfer to them, let them more organization in phase. And synchronously at this moment what is going on, this vector of magnetization, so this was like this direction, so what is going on, it's step by step, declining into perpendicular direction, and like in classic situation, it moves from this longitudinal to this transverse position. So this is excitation, Inside excitation, our rotation out of phase is turning into in phase, and the vector is rotating. This is the beginning, before excitation, so rotating out of phase, and the direction of the field is longitudinal, and this is after excitation, synchronous, in phase, and in this
Same
perpendicular direction. So this is the physical, this excitation. So why do they need whiz? Why do they need today extra energy? So the reason is that we need to produce some transverse magnetization, because the field is really strong, and our vector, which we organize from out the nuclei, is still weak, and we cannot measure it. But if we create some magnetization in another direction, not like inside this magnetic field, it will be measurable. And so that's why they are dealing with that. That's why we transfer energy. Actually, pay attention that in practice, we can transfer different amount of energy. We can control this. And that means that we can turn this vector on different degree, not every time on 90 degrees, but we can do it in a different manner, and we can create different sequences, MR sequences. So they will be shorter or longer, and will give us better pictures or like slower pictures, or sometimes they can produce like faster pictures, but more poor by contrast resolution, So we can work with that, and there is some information about this which can be understandable for you after next class. But I hope you will look through this presentation one more time after the second class, and probably you will understand this. I just want to introduce this term flip angle. So what is this flip angle? So this will be the degree of rotation, of this vector, and we can do it we can control it, And again, let's pay attention that this excitation is like this, from out phase to in phase, and from longitudinal to perpendicular. And of course, this is a whole thing. These are not two different processes. So this is going on like inseparably. But in order to understand what's going on and how we can teach, how we can study tissues, we need to understand, that inside we can think about these two components, So from out phase to in phase, So this is from out phase to in phase, And this will be our tissue characteristic, which we'll discuss sometimes later, which we'll measure, And this turning of the vector from longitudinal to transversal, it's another component. So they are like realizing, they proceed at the same time, simultaneously, and they're inseparably connected. But like we can think about them like two different things. Just think about, And so the last thing, relaxation. Does it look relaxed?
Yes.
Kind of. I'll try to choose the most relaxed face which I managed to have, So, and for at the same time, they are trying to understand, we are trying to understand what they are telling about them. Yeah. Again, pay attention that only hydrogen nuclei which were rotating at a certain frequency and absorb this radio wave energy, so only they will relax, so only they will tell us information about the tissues. Again, this resonance thing is the key thing. And so let's try to figure out what information can we get from this relaxation thing. Well, first of all, remember that only hydrogen nuclei relax. So if we can measure any signal, any activity, any radio frequency wave, yeah, that means that we find some hydrogen in tissues, that these are soft tissues with hydrogen, or that they are situated in the right place in the part of magnetic field which we structured to be this nuclear rotating this certain frequency. And so this is the first part of information. And another thing which is really simple to imagine, yeah, that the more the hydrogen in tissues, the bigger the signal, yeah. And this is actually the first tissue characteristic which is important to MRI. Yeah, it's named proton or hydrogen density. So this is about the amount or the quantity of hydrogen in tissues. Well, let's pay attention that usually in nowadays, at the beginning of the MRI, it was really important thing. That was at the beginning of the MRI. But right now, we mostly think about proton density like the necessary condition to catch real information. The process of relaxation, returning to the starting position, is connected with the tissue structures and hydrogen surroundings, interaction with hydrogens with surrounding tissues. And so that means that different tissue will relax with different speed. Moreover, pay attention that like in excitation process, so what's going on then it's relaxation. So first of all, in phase rotation is step by step turning to out phase, like in the beginning, the starting position. And what is going to the vector? It's returning to the starting longitudinal position. And so, like in excitation process, in relaxation process, we also can feel, and think about these two components separately. And actually it appeared that these components are connected with different details of tissue surroundings, of tissue structure. And so we can study two relaxation process and we can study their duration. So we can study two relaxation times, T1 and T2. So T1 is the time which the tissue needs to return to starting position, fully return to starting position. And T2 is the time during which this tissue can keep this transverse magnetization and this in-phase rotation. So these are two different types of relaxations which are different in different tissues and they depend on different tissue characteristics, tissue structures. So these are the names of these two new tissue important characteristics, relaxation time T1 and T2. And if this thing is connected with the quantity, amount of hydrogen, so this characteristic is connected with quality of hydrogen. So what do we mean by quality? That means that not good, bad or good. That means inside what tissues it's this hydrogen, in which molecules, and what is the surroundings. And so that is what is important for these relaxation times. Let's be more specific and have understanding of both these tissue characteristics, step by step. So the first one, like relaxation T1, relaxation 1. So again, so what is this? The returning, of this magnetization field into starting position from perpendicular, to longitudinal direction. Since it's returning, to this starting longitudinal direction, it has another name, longitudinal. And it has a very, very fancy, probably like scary name, like spin lattice. Well, let's translate what does it mean, spin lattice, to like human language, from physics language to human language. So what does it mean? That means like for all tissues, this time, this relaxation time, depends on how hydrogen, nuclei will exchange energy with their surroundings. So, and remember, we say that we can name hydrogen nuclei like spins, and the surroundings like lattice. And so that's why it's named spin lattice relaxation, yeah? And yeah, so what it depends on, yeah? It depends on like what are the atoms next to each other, hydrogen and all other atoms, what are the chemical bonds inside these molecules, what is the size of molecules and how mobile they are. And so you know what, these things are different in different tissue. And so that's why different tissue, yeah, return to starting position with different speed. For example, see, so this is how the fat is doing this, and this is how the water is doing it. So fat is doing it quicker than water. And remember, we can see fat and water in clear detail in these pictures, yeah? And if I think about some other tissues, for example, see, I add the tissues like white brain matter and gray brain matter. And so what do? They do it with a special speed, yeah? Different from fat and water. And see, we have 4 tissues which are returning in starting position, yeah, with different speed. And so if we are clever enough and choose the right moment to measure the signal, well, it's not a good idea to measure it like this because they will all produce the same signal. And in this moment, does it make any sense to measure the signal? No. But if we do it some here, we can have different signals from these tissues. And we can have them in different colors in other pictures. Yeah? So this is how this relaxation can work. Yeah? And it's about mostly about lattice, about surroundings, chemical environment. Like pay attention that since this is the returning to the starting position, so the quicker the process, the shorter the T relaxation time, the stronger the signal. Yeah. So if we measure them, who will have the highest signal? Fat. Yeah. Since it's doing it in the fastest way. Yeah. And what is T2? So T2 is the relaxation, the time, yeah, which is connected with this like preservation of this transverse magnetization of this in-phase rotation. Since it's about, yeah, like preservation of transverse magnetization, so it's another name, it's transverse and transversal. And see, it's another name is spin. How do you think why it's named spin? Not spin lattice, but spin. What it all depends on? Interaction between hydrogen nuclei and other hydrogen nuclei. Not the surroundings, but hydrogen and hydrogen. Spins. And what it depends on? Well, of course it depends on the size of molecules which are in tissue and their mobility. But what is important, yeah, so, yeah, so this is the same, yeah. But this thing is different. So here they see that this is the surrounding, but what is there? So this is dependence on homogeneity of the magnetic field. So if, yeah, the tissue is constructed of the same molecules like water, fat, so this magnetic field is homogeneous and it can keep this excitation for longer time. And if it's from different molecules, yeah, for example, like tissues, like soft tissues, mostly not water, not fluid, not fat. Or if there is something like, for example, like foreign body, like made from iron, or like hemosiderin, it's again iron, yeah, and it has properties like magnetic properties. So, and what they're doing with their tissue, making it inhomogeneous. And in this tissue, so this excitation, yeah, like can be lost really quick, yeah, because the field will be inhomogeneous. And see how it works. So you see like water and fat, yeah, are preserving this excitation for different times. Water longer, fat shorter. And if we add white matter and gray matter, what they're doing, they are also doing it with their specific times and different from water and fat. And what is also interesting, see, they are doing it in another manner. If they return to this graphic, yeah, so this is about T1. So in this graphic, brain matter, white and gray, are between fat and water, and in this graphic they are below. So what does it mean? That they are different in different manner. Can you think it? Yeah, different in different manner. And that means that we have many things, yeah, treat, yeah, so that to have the right signal from the right tissue, yeah. So this is all important moments in other possibilities to create a picture with a special color scheme, yeah, because they have differences and we can work with them, yeah. So let's try to summarize that. Well, let's go from these graphics. This is another variant to see these graphics. And again, see that this is fat, water, and between, yeah, white and green matter. And see, like this is water and fat, gray, yeah, and white matter. They're a little bit in different graphics because we are looking at graphics which are created in different magnetic fields, yeah, with different strengths of magnetic field. And right now let's see on this idea in numbers of relaxation times for different tissues, just like a certain number. So let's look at this table, and what do they see there? Different tissues and numbers of their relaxation times in milliseconds. This is measurable. This is a real physical quantity. So this is not philosophical thing. This is physical quantity which can be measured in numbers in milliseconds. Yeah, pay attention, what do we see there? So we see in the upper thing of water, a liquid, so something which has small mobile molecules. So what do they see there? Tendons, proteins, and this is ice, and ice like is representative of dense tissue, of crystallic tissue, like bones, for example. Yeah. And there are some structures like muscle, liver, fat, yeah, which has many molecules of more or less different sizes, like average mobility, average size, so they're in between, yeah. And so let's see what are their relaxation times. Well, first of all, what do they see? Yeah, we see that for each item, yeah, what is it? The T2 time is much shorter than T1 time. So that sounds reasonable because what is T2 time? This is preservation of excitation, and what is T1? This is the whole relaxation. Like sounds reasonable. The whole relaxation is longer, yeah, than partly, yeah, the process, yeah. So this is important, and that means that we have opportunities to measure them in different time points, yeah, because they have different duration, yeah. So this is the first point of my explanation. So when another thing, yeah, what do we see? We see that each this part discussion in next class, but just the very beginning. So this is our table with numbers. Remember, these are our graphics which we pay attention to, yeah. And let's translate. So like this is into this part of this graphic, so structures which have big immobile molecules and structures which have mobile small molecules and in between. So this is the area of macromolecules, this is the area of water and the area of something in between. And so for T1 we'll have this line. So yeah, the faster, the longer the T2. And yeah, if we speak about T1, so big, medium size, we'll see something like this. So we see another graphic. So this doesn't work like Hounsfield scale, but still some regularity to keep in mind. Yeah, so this is possible for, it's good for understanding. And remember, yeah, the faster they return into condition, so the bigger the signal. The longer they keep the excitation, the bigger the signal. And so that means, yeah, that there is differences. Yeah, the bigger the signal, the longer the time, yeah, between this T2 and T1 thing. And so let's try to turn it into kind of image, what we'll see, yeah, so in this picture. So for T2 image, this is a piece of T2 image of a brain with a tumor. Around this tumor we see edema, water. And what do they see? First of all, see air and bones. What do? They don't respond, so they are black. Yeah. And soft tissue, they respond, so they have colors. How do respond? Differently? Yeah, so T2 for water is the longest. They can keep this excitation the longest time. And what is the water color on the picture? White. Yeah? And fat, yeah, different, yeah, like average molecules, they have like average time. And what is fat? What is fat? It's subcutaneous fat. It's bright, but it's not so white, yeah, like medium color. And this tissue, with like tissue with much proteins, brain tissue. So what color do they have? Dark color, not so dark, yeah, like bones, because they produce signal but weak signal. And so we see them, yeah, in this color. So what about this thing? Let's see, yeah, how this works. I remember, so this is another connection, yeah, this show to the signal, brighter, white, oh, so sorry, dark, they don't produce signal, and this slightly gray like stripe inside bones. This is bone marrow, and it has fat, and see this, it has see the stripe. And what will be the water and the tissues with big molecules? They should be dark, yeah. And water is even darker than big molecules, yeah. Since they have different T1 times, yeah. And see that happens that we see water in white there and water in black there. Now contrast is just the technique. We just measure different things. So this is how it works, yeah, in this situation. Yeah. So this is how they use it. Meditation and pay attention to, you can meditate and use it for your answers if you will volunteer to produce like this mandatory, non-mandatory theory assignment. So I try to collect, like make some summary about relaxation, types of like representation of this nuclear magnetic resonance phenomenon. Yeah, so how do they use them? Yeah, like to organize, to represent information in the mind. Well, mostly we do pictures. We do what we name MR scan, yeah, or tomography. So we produce these tomograms, yeah, using nuclear magnetic resonance. And they can be very different because, yeah, we can do the produce based on proton density or memory slide.